On the Stad Peninsula, in western Norway, the number of outlying islands shielding passing ships from the weather is 0. Not a handful. 0. Everywhere else along that coastline, vessels have something to hide behind. Here, they have open water and rock and nothing in between. That single absence has made this section, by long record, one of the most dangerous stretches along the entire Norwegian coast. Norway's answer to it is not a stronger hull or a better forecast. The plan on the table is to send ships through a mountain, a canal, and a tunnel cut into the peninsula so vessels can bypass the exposed water completely. The interesting question is not whether a hole in a mountain is impressive. It is why taking the sea out of a sea route is the only variable engineers here can actually control. Start with what is firmly documented. The Stad Ship Tunnel is a planned canal and tunnel designed to bypass the Stad Peninsula in Stad municipality in Vestland County. That word planned is doing real work. It is a project defined on paper and in policy, not a structure you can currently sail through. The stated purpose is narrow and specific, not shorter voyages as a headline benefit, not tourism. The purpose is to route traffic around a piece of coast that is described as one of the most exposed areas along the entire Norwegian shoreline. That framing matters because it tells you which problem the engineering is being asked to solve. Exposure, not distance. The Norwegian coast works as infrastructure that nobody designed. Thousands of islands and skerries sit offshore, and the water behind them functions as a sheltered corridor. Ships move up and down the country inside a natural breakwater that has been there since the ice retreated. Stad is the gap in that system. The source record is explicit that the peninsula has no outlying islands to protect it from the weather, and reasoning from that, the consequence is straightforward. When a vessel reaches Stad, it leaves the protected corridor and meets the open Atlantic without any intermediate structure absorbing the sea state. Everything difficult about this project comes from that one geographic fact. You cannot build islands into deep exposed water at a scale that would calm an ocean. You cannot armor a headland into a harbor. The shelter that exists everywhere else simply is not available here. For most of the history of this coast, the response to Stad has been operational rather than structural. That is an interpretation, not a documented policy, but it follows from the constraint. When the hazard is weather and the route cannot be changed, the available choices are to wait for a window, to accept elevated risk, or to move cargo some other way. Waiting is a real cost, even though it is invisible in construction budgets. A vessel that holds position for a day is a vessel not earning, and a schedule that depends on the Atlantic is not really a schedule. Nothing in the available evidence establishes earlier attempts to fortify or bypass this stretch, so I will not claim any. What the evidence supports is the durability of the problem. This section has traditionally been dangerous, and tradition here means it stayed dangerous. The turning point in the thinking is a reframe rather than an invention. Instead of asking how to make an exposed piece of sea safer, the plan asks whether the ships need to be on that piece of sea at all. Weather acts on a water surface. Rock does not have weather. If you can move the passage from the surface into the interior of the peninsula, you have not defeated the North Atlantic. You have simply stopped negotiating with it. That is the conceptual move that makes a ship tunnel rational rather than theatrical. It converts an uncontrollable variable, sea state, into a controllable one, traffic management inside a fixed structure. Strip the Stad Ship Tunnel down, and it is less a tunnel problem than a geometry problem. A canal and tunnel cutting across a peninsula connects two points that are already part of the same sea, at the same level. When both ends sit at sea level in the same body of water, the water inside behaves as an extension of the water outside, which removes the need to lift vessels the way a mountain crossing canal must. The structure of the tunnel itself is the mountain. In hard rock excavation, the surrounding stone carries the load, and the tunnel is the absence you create inside it, with support added where the rock is weak or fractured. The governing dimensions are set by the largest vessel intended to pass, measured to the top of its superstructure and the bottom of its hull, plus clearance. The specific figures for this project are not established in the evidence I have, so I am not going to assign numbers to them. What is established is the logic. The vessel size you want to admit determines the cross-section, and the cross-section determines how much mountain has to be removed. Tunnels that carry a world first have a history of charging for it. The Holland Tunnel between New Jersey and New York is named after Clifford Milburn Holland, its initial chief engineer, who died suddenly in 1924, before the tunnel he led ever opened. The record credits that tunnel as a world first in mechanical engineering terms, and it does not establish a cause of his death, so I will not imply one. The point is narrower and still worth stating. First-of-its-kind tunnels are built by named individuals who carry unsolved problems for years, and the finished structure often outlives the people who resolved them. A ship tunnel through Stad would carry the same profile. Excavated rock has to go somewhere. Entrances have to be maintained against the same sea the tunnel exists to avoid. And once the passage is committed to stone, the decision is effectively permanent. There are open questions that the available evidence does not close, and pretending otherwise would be the easy mistake here. A tunnel is a single channel. Traffic that arrives from both directions has to be sequenced, which means the passage becomes a scheduled resource rather than open water. Whether the safety and reliability gains justify the construction is a judgment call, and I have no cost figures, no timeline, and no completion date in the source material, so none appear in this script. The honest status is this: the project's purpose and location are documented. The physical rationale is strong and follows directly from the geography, and the economics remain outside what this evidence can settle. Norway is not, however, unfamiliar with the underlying commitment. The Rogfast undersea tunnel in Norway is documented as having entered construction, which shows the same institutional pattern applied to roads. When a crossing is exposed or unreliable, move it into rock beneath the water. There is a useful observation in the record about fixed links generally, which is that infrastructure like bridges and tunnels represents a much more concrete commitment to sustained service than the alternatives it replaces. A ferry can be cancelled in a storm. A tunnel cannot be cancelled at all. That is the real product being purchased at Stad. Not speed, certainty. Which leaves the lesson, and it is a structural one rather than an inspirational one. The Stad Peninsula cannot be sheltered, because the islands that protect the rest of the coast do not exist there, and no reasonable structure can substitute for them. So the plan stops trying to fix the sea and changes the medium instead, trading an unpredictable surface for a predictable one and accepting the cost of permanence in exchange. If it is built, the significant change will not be the tunnel. It will be that a stretch of coast that has always dictated terms to shipping becomes a passage that people schedule. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.